Okay, this video will start chapter 17. Chapter 17 is all about aqueous equilibria. Our bloodstream is an example of an aqueous solution that is in equilibrium and it doesn't change pH very easily. We call those buffer solutions, so we will certainly learn about those. So unit 1 or section 1, we're just looking at what a buffer solution is. We'll learn about equations to calculate the pH of buffer solutions. And then we'll learn about some titrations. You may have started titrations in lab. If not, I'm sure you will do them soon. And then we'll learn about a couple of other things towards the end of the chapter. But as usual, let's just worry about 17.1 for now. So we'll understand buffer solutions, explain how they work, and then calculate pH changes in buffer solutions after adding a strong acid or strong base. Okay, so buffer solutions, what this actually means. These are solutions that resist change in pH by neutralizing acids or bases. So a buffer solution itself is composed of weak acids and bases. And so if other acids or bases are added to that buffer solution, the pH of the solution doesn't change because acids and bases that are already in the buffer solution will react with the added acids and bases. So some examples are human blood. Our pH is about 7.4. That would be bad if human blood pH would change easily because our body should operate at this pH. Ocean water has a pH of 8.1. Baby lotion has a pH of 6. There's a lot of different buffer solutions out there that just have different pHs, but what they have in common is that they resist change in pH. So we need to understand this common ion effect to understand how buffer solutions work. So consider adding HNO2 to water. This is a weak acid. Well, why don't we write that down? Just to understand, it's weak acid. If it's added to water, it is in equilibrium. So we have our equilibrium arrow, and it's the acid, so it donates the proton, becomes NO2 minus, and then we get H3O plus. So we have this solution. We're thinking we've got HNO2 present, and then what if Na, sodium NO2, is added to the same solution? What would happen to that solution? Well, this would dissociate into Na plus and NO2 minus. Na plus is a spectator ion. NO2 minus is the conjugate base of HNO2. We saw NO2 minus right up here. And so with more NO2 ions present in solution, if we're adding NO2, we're increasing the amount of those ions, the equilibrium would shift left. This is Le Chatelier's principle. So we could say the ionization of HNO2 is suppressed by the addition of this salt. The addition of this salt suppresses the ionization of HNO2 because this salt increases NO2 minus concentration, and that would shift the equilibrium left, meaning less HNO2 is ionized. So continuing on from this, buffer solutions, this is an example of a buffer solution that contains both HNO2 and NO2 minus. So a buffer solution has significant quantities of both a weak acid and its conjugate base. Or we can say a weak base and its conjugate acid. Basically, conjugate pairs. So an example is if both nitrous acid, HNO2, and sodium nitrite, NaNO2, or in general, just NO2 minus, this polyatomic ion, are added to solution. Having both acid and conjugate base or base and conjugate acid present in solution allows the equilibrium to shift in either direction according to Le Chatelier's principle when other acid or base is added. Here's a diagram showing a buffer solution and then what happens when you add a acid or base. So buffer solution has both acid and conjugate base. Here's the acid. It's represented just as HA. This is the acid's conjugate base. And it has generally even amounts of both at equilibrium, or when it has become a buffer solution. In this example, it has equal amounts. If you add acid, that will shift the equilibrium to the left and you end up with more HA because the acid would donate a proton to A minus that's present in solution, and that would form more HA. Or if in a buffer solution base is added, the base will react with HA to form more A minus. So there would be after adding base, more A minus present than HA or than there is without having added the acid or base. But even with the shifts, the pH of the solution changes very little because there's already a very large amount of both the acid and the conjugate base. So let's do a learning check here. It says, which of the following combinations of species will result in a buffer solution? So I would encourage you to pause and try this on your own before we go through it together. But thinking about what happens when HCl and NaOH, hydrogen chloride and sodium hydroxide, are added to solution. Well, the hydrogen and hydroxide would combine to form H2O, and sodium would remain a cation, a spectator ion, and chloride would remain a spectator ion as well. These are both a strong acid and a strong base, so it's not going to make a buffer solution. They will just completely react. They won't reach an equilibrium. So the answer to the first one is no. This is a strong acid and a strong base, and we need a weak acid and a weak base, and they are conjugates of each other. How about HCO3 and CO3 2-? Well, these two ions differ by one H plus. One has the H plus, one doesn't. They are conjugates of each other, and neither one is a strong acid or strong base. So yes, this one will work. So that could be those could be used to make a buffer solution. Last option is hydrogen bromide and sodium bromide. Well, HBr, this is a strong acid. So this cannot make a buffer, even though they are a conjugate pair. We have an acid and a conjugate base as Br minus, it's Na plus and Br minus. This one's a strong acid. It fully ionizes, so it would not reach an equilibrium. All right, let's do the next learning check as well. 2 parts. So we have this question and then a follow-up question after. So this says ammonia, NH3, and ammonium chloride are combined to form a buffer with initial concentrations stated there. We have Kb of ammonia. Then we're calculating the pH of the buffer. So let's understand how these two are related. We can hopefully see these are conjugates of each other. A weak base, NH3, if that is reacted with water, it forms NH4 plus and OH minus. It's a weak base. It says, well, it doesn't say weak base, but we have learned in class that NH3 is a weak base. So this is the base. This is the conjugate acid. And ammonium chloride is that conjugate acid with a chloride ion. So we have a base and conjugate acid added together to form this buffer solution. We have initial concentrations, and we are trying to find the pH of the final solution. Well, we have an equilibrium reaction. We need to find equilibrium amounts. Got another ice table. Leaving water off since it's not part of the equilibrium reaction. I'm sorry, not part of the equilibrium constant, K. All right, set up the table. Now we have initial concentration of NH3 is 0.21 molar and NH4 plus is 0.14. Then we can assume 0 for hydroxide. Because there is no hydroxide present, the reaction will have to go to the right to reach any equilibrium. If you were to calculate Kb, for example, with initial concentrations, or I guess it would have to be Q because it's not K yet, we would have products 0.14 times 0 for hydroxide divided by 0.21. So Q would be 0. That is less than K, so reaction proceeds to the right. So we use up some NH3, produce some NH4, and produce some hydroxide. We have the Kb value, the Kb of NH3. So we will use that to find equilibrium amounts. So Kb, concentration of NH4 plus times concentration of OH minus divided by concentration of NH3. And this is all at equilibrium. We don't have any equilibrium concentrations or information other than Kb. So we have to solve these in terms of X. So this is 0.14 plus X times X divided by 0.21 minus X. Well, these are both weak acids and weak bases. NH3 weak base, NH4 weak acid. Each of these would dissociate very little, so the change, the X value, is going to be very small. So these two factors can be approximated as 0.14 and then 0.21. Just like we did last chapter for weak acids and bases, you can assume 0.14 here times X and then 0.21 in the denominator, making this calculation more simple. And this will be equal to 1.8 times 10 to the negative fifth. That is the Kb value given to us in the question. All right, solving for X. Multiply both sides by 0.21, divide by 0.14. I calculate X equals 2.7 times 10 to the negative fifth. That is the OH minus concentration at equilibrium is just equal to X. And remember that we're looking to calculate pH. So if we find OH minus concentration, we can find POH and then calculate pH from there. So I'm going to start working in the top right of the page now. So POH is negative log of OH minus concentration at equilibrium, which we calculated by finding X. So POH is equal to 4.57. That means pH is 14 minus 4.57. That is 9.43. And that's our final answer when asked about the pH of this solution, of this buffer solution. Okay, next we have this question. How does your answer change if you treat the initial concentrations as equilibrium concentrations and plug them directly into the Kb expression? So let's say we don't do the ice table for this buffer solution, and we just say the 0.14 and the 0.21 are the concentrations at equilibrium. Well, we could then just calculate use Kb to calculate OH minus directly. So remember, Kb was NH4 plus concentration times OH minus divided by NH3. If we plug in values that we know, this would be 0.14 times OH minus, we don't know that concentration yet, divided by 0.21. Set this equal to 1.8 times 10 to the negative 5. That's the Kb value. We're doing the same thing we did after the ice table, the same calculation. So multiply both sides by 0.21, divide by both sides by 0.14. We get OH minus is equal to 1.8, it's equal to 2.7 times 10 to the negative 5 molar. If we go back to what we did on the previous page, we got the same concentration here. It's because we're working with weak acids and bases, and we can approximate these factors with that x being approximately 0. This here is the same where we're just looking for x, but we've got 0.14 times the variable divided by 0.21 equals this. Same as this calculation that we did here. Then we could find POH and find pH, and we get the same answer. So I'm just going to write a little note here. Same as previous slide. So when I teach this in person, I sometimes get dirty looks from students because we just did this whole ice table problem. But for buffer solutions, you don't actually need to, which is really nice. So let's write this here for buffer solutions. And buffer solutions only, so this doesn't apply to the other ice tables we've done, just for buffer solutions, you can assume equilibrium concentrations are nearly equal to initial concentrations. So maybe the question comes up, how do you know you're calculating the concentration for a buffer solution? It'll either say in the question that it's a buffer solution, or if you notice that both a base and conjugate acid or acid and conjugate base both are added to solution, then that will be a buffer solution. We actually have an even more direct way to calculate pH. Remember, that's what the original question was, to calculate pH, using the Henderson-Hasselbalch equation. So we can use this to calculate pH of buffer solutions in a little more direct way. This equation relates pH Ka in acid-base concentrations for a buffer solution. So for example, if we have this example buffer solution, acid, this will be base, conjugate acid, conjugate base, then the pH of that solution is the pKa of the acid, so that's, remember, negative log of Ka, plus the log of this fraction, conjugate base over the acid. We can use this under this assumption that we just talked about. Equilibrium concentrations are approximately equal to the initial concentrations. So let's do this learning check. It reads very similar to the one where we did the ice table, but now we know we don't need to do the ice table. So it says calculate the pH of a buffer that contains 0.170 molar formic acid and 0.120 molar sodium formate. And then we have the Ka of formic acid. We might not know the formulas for formic acid or sodium formate. Maybe you do. But even if you don't, we know that this is the acid and this must be the base. We know this is acid because it says formic acid. This is sodium, and then that will balance with the base, A minus, for example. Just like the last slide where we had HA as a generic acid, added to water, forms H3O plus and A minus. So we know there is 0.170 molar HA and 0.120 molar A minus. So using the Henderson-Hasselbalch equation, we have pH equals pKa plus the log of the ratio of conjugate base to acid concentrations. So this is negative log of 1.8 times 10 to the negative 4 plus the log of 0.120 divided by 0.170. So I get 3.74 plus negative 0.151, so really 3.74 minus 0.151, 3.59. And that's the pH. This equation is on your periodic table and equation sheet. So you can always use that as a reference when you're working through questions like this. All right, let's do another learning check, see how else we can apply Henderson-Hasselbalch equation. This says calculate the relative concentrations of acetate ion and acetic acid that must be used to make a buffer solution with pH of 4. Then we have the Ka of acetic acid. When they're asking about relative concentrations, this is really asking about a ratio. And it's the relative concentrations of acetate and acetic acid. So that would be the base to the acid. So ratio of A minus to HA concentrations. Which is nice because our Henderson-Hasselbalch equation, that's the fraction that's in the equation. So using pH equals pKa plus the log of A minus over HA. We want to solve for that fraction, what the ratio is from A minus to HA. Acetate, in this case, to acetic acid. We have the pH of 4. That's the goal of the solution, is to make a pH of 4. So we need to know how much acetate to add per acetic acid amount. So this should be equal to negative log of the Ka plus the log of this ratio, which we don't have, so we will be solving for that ratio. So just adding values in, we'll go stepwise here. I get the pKa is 4.74. Subtracting 4.74 from both sides, I get 0.74 is equal to log of this fraction. Remember that that log is base 10. So if we need to eliminate that log function, we need to raise both sides, or we need to raise 10 to the power of the value on each side of these equations. So 10 to the negative 0.74 is equal to this ratio, A minus over HA. And this is 0.18. So that is the relative concentration of acetate to acetic acid. For every 1 acetic acid, you need 0.18 acetate ions. Okay, so those are a couple ways to apply the Henderson-Hasselbalch equation, calculating pH or calculating relative amounts based on your desired pH, like 4 in this case. For buffer solutions, some are better at resisting change to pH than others. So how well the solution can actually resist change depends on 2 factors. The first we call buffer capacity. And the second is its effective pH range. So we'll talk about each of these. Buffer capacity is the ability of a buffer solution to resist change in pH when an acid or base is added. And so a buffer with a higher concentration of conjugate acids and conjugate base will resist a pH change more strongly than a buffer with a lower concentration of that conjugate pair. So higher concentration of acid and conjugate base will resist change in pH better, more so, than a buffer with lower concentrations. Also, buffers resist pH change most effectively when the concentrations of acid and its conjugate base are equal. So when the concentrations So for example, with this equilibrium reaction here, HA, again, we're just talking about generic HA with conjugate base A minus. If equal amounts of HA and A minus are added to solution, that will be a better buffer solution. It'll more so resist change in pH. The effective pH range is related to the acid pKa. So buffers are optimally effective at a pH that is numerically equal to the pKa of the buffer's acid. So the best pH, or the buffer, is most effective at a pH that is approximately the pKa of the acid HA. So buffers are typically useful at pH values that are within plus or minus 1 of the conjugate acid's pKa. So the situations where something like this would be applied is if you are looking to generate a buffer solution that has a certain pH. Like if you want the pH, you could select different acids and conjugate bases, but you know you want the pH to be 5. Then you want to find an acid that has a pKa of approximately 5. Here's a learning check applying that. It says, which of the following weak acids could be used to buffer a solution at pH 10.8? Well, we're looking for an acid that has a pKa near 10. So we would have to find the pKa of each of these acids. I have found a couple already. Remember, we're just taking negative log of the Ka. Acetic acid pKa is about 4.74. Boric acid is about 9.23. Notice that the pKa is pretty similar to the exponent. So this one's 5, the pKa is almost 5. This one's 10, pKa is almost 10. This one's 4, so the pKa will be near 4. Same with hydrofluoric acid, same with nitrous acid. So let's try phenol, because I know that these pKa's are not going to be close to 10.8. You could still calculate them just to double check. But the pKa of phenol is 9.96. So of the options in this table, this will be the best option. So it's the best option because the pKa is closest to 10.8. All right, let's do one more learning check. We'll calculate the pH of 1 liter of a buffer solution containing 0.150 moles of acetic acid and 0.195 moles of sodium acetate. We know this is HA, acetic acid. Sodium acetate is A minus. We have Ka for acetic acid on the previous slide. So we're really just applying Henderson-Hasselbalch equation again. We would expect the pH to be close to pKa, although we're not adding equal amounts of acetic acid and sodium acetate. But we would expect the pH to be near 4.74, near the pKa. So let's see what we get. On my reference slide, I don't have the values for each of these. I just have the actual pH, and I have 4.86 as the pH of the solution. Again, we'd expect it to be close to 4.74, which it did. So that aligns with what we would expect. Okay, we'll end the video here. I'll see you all in class and we'll start 17.3.